All right, two more to go. First, Nataly Brukhim.
Thanks. So I work on theoretical machine learning, and I'll talk about a very fundamental result in learning theory and some generalizations of it. So one of the most basic problems that you can think of in machine learning is that of classification. So we're given a bunch of classified data points. So these are this is a pair of X and Y, where X could be from some set X of, let's say, all possible images of cats and dogs, and a label Y, which is 0 or 1, let's say 0 if it's a cat and 1 if it's a dog. And then we want to be able to classify correctly a new unseen example. We can think of this problem in a matrix form, where the columns of this matrix correspond to all data points that we can observe from our domain X. And the rows of the matrix correspond to possible labeling that we're considering. So these are just binary functions of our domain, over our domain. And and this is a restricted set of binary functions that we call our hypothesis class H. So now I'll describe what does it mean to be able to learn a function from this class. And this is the standard model in machine learning called probably approximately correct, or PAC learning. So learning in this model corresponds to the following. I'll describe an algorithm by describing its input and its outputs. The input to the algorithm is a training set S of M data points, where the data points M come from sampling IID from some distribution D over the columns, which is unknown to the algorithm. And they are labeled by some function H star, which is the correct labeling. It's some row in this matrix H star.
Nataly, I suggest something radical. This half the audience was not there when you started. I suggest to start now, and for the benefit of everyone. For you, I guess clock were not synchronized. So if we have only 2 talks, you can start your 15 minutes now.
Okay, I'll start again. Okay, so I work in theoretical machine learning, and I will describe a fundamental result in learning theory and some generalization of it. So a very basic problem in machine learning is binary classification. So we're given a bunch of classified data points. These are pairs X and Y. These X's come from some set X, which could be, for example, images of cats and dogs. And we have a label for them Y, which could be 0 if it's a cat, for example, 1 if it's a dog. And then we want to be able to classify it correctly, a new unseen example X. And we can represent this in a matrix form. So the columns of this matrix correspond to all of the possible data points that we can have. So for example, all possible images of cats and dogs. And the rows of the matrix correspond to all possible labelings that we can assign for them. So these are just, this is a set of binary functions that we're considering. And I call this set of functions a hypothesis class H, and I'll describe to you what does it mean to learn a hypothesis class. So this is a very fundamental model in machine learning called probably approximately correct, or PAC learning. And to describe what does it mean for an algorithm to learn, in small, I'll describe the input and output of this problem. So the input is a training set S of M data points, sampled IID from some distribution D over the columns of this matrix that is unknown to the learner, and is labeled by some function H star, which is some row in this matrix that is also unknown to the learner. So essentially the learner only gets to observe a bunch of these columns and they're labeled. Okay, and we need to find the correct labeling. So what is the output of the algorithm? It's just a classifier, another binary function. And the goal of the learner is to be able to have a low error over the same distribution D that was over the columns, where the error is what you would expect, is the probability of H and H star disagreeing expected. Okay. So specifically a notion that we care about in this context is that of PAC learnability. So what does it mean for a hypothesis class to be PAC learnable? We say that H is learnable if there is some function M, where M is sometimes referred to as the sample complexity of the class, and there's some learning algorithm. such that for every parameter epsilon between 0 and 1, so this is the error, and given m of epsilon examples, so this is the size of the training set, the output of the algorithm would have error at most epsilon.
And this should work for any distribution.
And this should hold for any distribution. Thanks. Right, so a basic question that we can ask here is which classes H have this property of being learnable? Maybe it's not a natural question to ask, or maybe it's not, maybe we wouldn't expect for such a simple question to have a clean answer, but in fact, there is a pretty simple combinatorial parameter over the class H that essentially answers this question in a very clean way. So I'll describe this parameter now. It's called the VC dimension after Vapnik and Chervenenkis. And it's essentially the largest number of columns D in this matrix, such that restricting the matrix to these columns forms a complete D-dimensional Boolean cube. So this is easiest to see with an example. So in this case, I have that the VC dimension is these two, because there are two columns, these red columns, that have all of the possible combinations of zeros and ones. There are 0, 0, 1, 1, 0, 0, 1, and 1, 1. And in general, if I had D such columns with all possible 2 to the D combinations, I would say the VC dimension is D. Okay. So indeed, this gives us what is sometimes called the fundamental theorem of PAC learning, and essentially says that a class is PAC learnable if and only if its VC dimension is finite. And not only it characterizes this notion of learnability, it also gives us the optimal sample complexity. So this m of epsilon that we talked about earlier is essentially D over epsilon, where D is the VC dimension of the class. So a bit more generally than that, the VC dimension also has connections to many other areas beyond learning theory, for example, discrete and computational geometry, complexity theory, combinatorics, and more. So this is all very nice, but there's a basic extension that we might wonder about. So what happens if the number of labels in our class is larger than 2? So if these are not just binary functions, but if we have multi-valued functions, what can we say about that? In machine learning, this is called the multi-class PAC learning setting. So we have a matrix like before, but instead of having binary values, we have all kinds of values there, and we can think of some bounded set of labels, or we can even think of unbounded sets of labels, for example, all natural numbers that we can expect to see. And we can ask the same question that we had before. So which classes H are learnable? We would hope to get a parameter that is similar to the VC dimension that kind of captures learnability in this more general set. So indeed, in the late 80s, then Natarajan proposed this natural generalization of the VC, which comes from a generalization of just the notion of a Boolean cube. So we can say that an Natarajan cube is a D-dimensional Natarajan cube has two different labels, A1 and B1 up to AD and BD, such that we can expect to see all of the possible combinations from each of these D clauses. So for example, here I have D equals 2, where the two labels for the first column is 1 and 2. The two labels for the second column is 0 and 1, and I have all of the possible combinations of these. So this is just a renaming of the labels of the Boolean cube, and we call this like a copy of the Boolean. Okay, so what can we say about this dimension? So indeed, we get a result that is very similar to the one that we had in the binary case, which says that H is PAC learnable if and only if its Natarajan dimension is bounded. But the caveat here is that this result holds if the number of labels is bounded. And we cannot generalize this result for the unbounded case. And not only that, even if in the bounded case, the sample complexity, this m of epsilon that we had before, now has this extra factor of log number of labels. So there's a gap between the upper and lower bounds on the sample complexity here. Okay, so we're interested in generalizing this to unbounded sets of labels. And this turns out to require a new notion of dimension. So for this, we will turn to another representation of our hypothesis class. So for now, just imagine our matrix from before, but now it's just a finite matrix. And I will describe how to turn it into a graph, or to represent it as a graph or a hypergraph. The nodes of this graph would be the rows of the matrix. And there's an edge or hyper edge connecting several nodes if they differ in exactly one coordinate I. If there's a coordinate I on which they differ. For example, the blue hyper edge connects all these three nodes because they disagree on the leftmost blue coordinate. Okay, so why is this useful? Now we can identify this other property of a Boolean cube, that if you look at the leftmost plot, you can see that a Boolean cube is just a deregular graph in this model, right? We can, in this generalized model of the Hemming hypergraph, which I just defined, we can define the notion of a pseudo cube, which is another deregular graph. So in this case, a Boolean cube is and pseudo cube coincide in the case of two labels, but when there's more than two labels, these are different. Okay, so a result with Kalmon, Dino, Moran, and Yudayov, we show that a class is PAC learnable if and only if the DS dimension, which is essentially the largest pseudo cube you can find, is finite. So in fact, we generalize this notion of the VC dimension, the more general case, when the number of labels is unbounded. This also gives us a better bound on the sample complexity. So we have that M of epsilon is D to the 3/2 over epsilon. So we got rid of this log number of labels factor that we had before. And one more thing to note, which I don't have time to talk about much, but the Natarajan dimension that I introduced before, and this pseudo cube notion that I introduced now, actually happen to be very, very different. And there we can show a construction in which the gap between those is arbitrarily large. And this is based on a deep and involved construction in algebraic topology, in which you can construct an object with a very large pseudo cube and a bounded constant Natarajan cube. And one last thing, an open question is whether we can improve the bound from D to the 3/2 to D so that it would match the lower bound. This is a nice thing we would want in learning theory, but it also hides this interesting combinatorial question relating to pseudo cubes and graphs that I'm happy to talk about offline. That's it.
Question.
Is there an obvious inequality between the Natarajan dimension and the pseudo cube? Like it's always smaller than Natarajan?
Yeah. So the pseudo cube is always larger than Natarajan and always upper bounded by Natarajan times log number of labels. So it's like sandwich between them. But when the number of labels is infinite, then this is kind of a vacuous upper bound.
So what is the difference between like a multi-class and multi-label and like multiple binary labels? Like you classify like 1, 2, 3, 4 versus use multiple binary things.
So you're asking whether I can use different binary functions to represent a multi-value function?
Yeah.
Yeah. You can do that. In this case, we restrict the function class and we say that the true label has to come from one of these binary functions, so not an aggregation of multiple binaries.
I have a question. So the algorithm, the learning algorithm in these extended parameters, Natarajan and pseudocubes, are they also like Occam razor? Take the simplest solution?
That's a good question. No, so in the binary case, we have a very nice algorithm that just says, look at what you're doing best on the training data. That's going to be a good learning model. No, so that's not true when you have multiple. Yeah, that breaks.
Oh, question. All right, thanks.